Alright folks, in this lesson we're going to talk about one of my favorite topics, and that is structural steel fabrication. Okay, I do enjoy this. I get to design this kind of stuff a lot, and I really like it. I really like putting stuff together. And to understand structural steel, it's simply, and most of you are probably familiar with several of the components that we usually involve with structural steel. And what we're talking about here is structural steel for the purpose of building, larger things. For example, high-rise buildings made out of steel frames, a lot of X-bracing, a lot of kickers as we call them. Even trailers are made out of structural steel, bridges, beams, those kind of things. So we're dealing with the big stuff. And structural steel is broken down to several different types of parts, different cross sections, different shapes. And one of the things you have to understand is in terms of like how the stuff is made, structural steel is what we call cold rolled, which means that the process for making some of these beams and tubes actually occurs in a cold rolling process. Now, one of the reasons that we do this is simply to actually increase its overall strength. There's actually advantages to shaping things with, and when they say cold, they're not actually freezing it or anything. They're actually just using it without heat or without much heat. There's like heat limits on what is considered cold or hot rolled. But essentially, cold actually builds up certain levels of strength properties versus doing hot rolling. So it's a crystallization effect we won't get into, but just so you understand, when they say cold rolled steel, they're referring to most of the things that we consider fabrication steel. But let's get right down to it. One of the most common things that people are used to thinking about when they think about big steel buildings is they're used to thinking about this shape right here. The good old-fashioned steel beam. All right? A little break line there for you. Now, most everybody will turn around and call this an I-beam because of its shape. And in truth, its cross-section is shaped like an I, for sure. We'll talk about why in a little bit. But the problem is, in structural steel, we actually don't use I-beams that often. We use what were called W-beams, which stand for wide, as in W, wide flange beams. By the way, this is the flange, and this is the web. So there's the web, this is a flange, and this is a flange. The reason they're called wide flanges is because they have a lot of more width. Now, there are such things as S-beams or I-beams, but they're actually a little bit more shaped like an I. For example, this you could probably get by with calling an I-beam. However, we don't use that nearly as much in structural fabrication than we do the W-beam. So whenever you see the wide flanges, whenever the flange is much wider in proportion than kind of this narrow profile that you see right here, it's a W-beam. And like I said, in most steel fabrication, it's going to be a W-beam. The reason we actually like W-beams in steel fabrication and why they're shaped to be wide, why they have that wide flange, and this is just going to be a little lesson in engineering mechanics, or deformable solids as we actually like to refer to it as. The reason these are wide up near the top versus having like a nice little narrow flange is because when you actually take a beam and you span it across, draw a little shape here, you take a beam and you span it across like a big open space and you stand in the middle of it, the beam gets stressed, for example, and you know this, if you actually go take like a piece of wood and you stand it over like a space, however big, 5 feet, 2 feet, whatever, and you stand in the middle of it, what's it going to do? Well, it's going to deform like this. It's going to bend downhill, right? That makes sense. It's going to sag. Perfect sense, right? Now, the reason it does that is because of the material properties associated with the beam and also its overall shape. You see, shape and material make up the real nuts and bolts of why things perform structurally speaking. And if we were actually to look at this beam, we would find out that some of the greatest stresses of the beam are occurring at the very top and the very bottom of the beam. So for example, when you span over a big space like this and you put weight on it, we'll just call it, let's say we're putting 10,000 pounds on this. And we're pushing down. This, right in this zone here, and here is where the greatest stresses are going to be. And if there's great stress, that means we need to have more material to resist that stress. Therefore, to compensate for the problem, we have a really thin web. Again, the web is this section right here. And we have really, not so much thick, but wide. So we get more material up here to resist the bending stress, that's what that was referred to, or flexural stress. So by adding in material here versus a narrow beam, normal flange beam, by adding in more material, we can handle more stress with not a lot of extra weight. So that's different than just adding like a big old chunk of material, like a big old piece of wood. The point is, a big old piece of wood cross section doesn't have, hey, it does have strength right here for sure, but it has a lot of wasted material in this zone that we don't actually need. So that's why the beams are shaped this way. We maximize where the stress is with material, and we omit in these zones where we don't really need material. So that's why W-beams are so common, because they support long bending loads very effectively. All right, so there's your quick understanding of W-beams as to why they are shaped the way they are. And W-beams you'll see all the time in building plans. For example, well, I think I've got a graphic right here. Yep, there's one. So this is a pretty common graphic. What you're seeing right here, of course, is a W-beam that's being used as a column. And then we've got a beam right here. And we've got a different size beam right here. I can't really tell what they are though. They look like almost like they're rectangular, but they could be W-beams, can't tell by the thing. But we use W-beams oftentimes for columns and for beams. Now we also use steel pipe and square tube for columns, but W-beams serve to be, are very common in steel fabrication for columns because of their shape and overall strength. Now up here, just for the record, we have what we refer to as open web steel joists, which those are actually not, those are a big assembly. Let me draw something right here if I can, find a space here. Open web steel joist systems are, what they look like is a typical truss, which you're probably used to seeing that, but they're actually made out of steel. There's typically some pieces of angle up here at the top and on the bottom, and there's a steel bar that runs up and down like this. Okay? They usually sit on frames like that, and there's no connection here or here. They just kind of hang out in space. But those are open web steel joists, which is what you see in the picture. But anyway, we're still talking about W-beams for right now, so we'll just stick to that first. So, on a set of plans, sorry, I'm throwing too much information at you at once. On a set of plans, you might see a steel drawing. Let's show it. Let's say here's a column, and this would be in like a blueprint of a building plan, like a floor plan, if you will. And you might see something like this, where you see a line going this way and a center line going this way, and you're going to see some kind of like little block or circle, and you're in a plan view. So this is a floor plan of a building. This, of course, would be a column coming out of the page at you, coming up. And this might be the beam. And what they'll do is they'll say, all right, we're going to do a W12 by 26 or 22. I can't remember which size. I'll have to check to make sure I'm giving you the right size. But this is typically the way that W-beams are specified. The W, of course, stands for the wide flange beam. The 12 stands for the nominal height of the beam. That would be this value right here, 12. So if this were a taller beam, if it was this tall, and say it's 16, it would be a W16. So your first dimension associated with a call out on a beam is the actual height of the beam. Now this is confusing, this part of it. This, you may think, well, that's some kind of like width measurement or something. It's actually not. What the second dimension value represents is the actual weight per foot of the beam. So we'll just say pounds per foot. So what it means is that this particular beam that's being used on this plan is roughly 12 inches tall and weighs 26 pounds per every foot. So if this were 10 feet apart, then of course the overall weight of the beam would be what? Yep, 260 pounds. So that's another thing about steel. Steel is often priced and calculated by its weight more so than anything else. So steel beam, how would you know what width it was? Well, you'd have to use some charts and manuals to find out what wide flange dimension this is. And there's plenty of those out there. But this is probably the most crucial component to the whole system, is the weight of the beam and how tall it is. The height gives you some head clearance for sure, and this is structurally important because this is how you're going to put the thing together, how much it's going to weigh on its own. And these things can get up to several hundred pounds per foot. I mean, you can get some massive beams. So there'd be W12, 26, there could be, I can't remember if a W12, 26 exists or it's a 22, it's something like that. So flipping on over real quick for a graphic. This shows what I'm talking about. This is essentially the call out. Right here they're showing a W18 by 76, meaning it's 76 pounds per every foot. This is the depth as mentioned. And like I said, this is the flange, this is the web, and this is the flange 2, and of course the flange width is this way. But you don't get this in a call out, you have to look that up. Beam shape right here, as you're seeing it's a W. There is also an M shape, an S shape, and even an HP shape. And you can check those out with internet resources to find that information. But again, most likely, actually you'll probably see these two most likely. I've seen M's and S's pretty often. You may see an S, but you know, more than likely on a set of plans in structural steel, you're going to be dealing with W beams. But this is essentially how they show it to you. You've got a floor plan, view of something. Let's just say we're framing some kind of steel building just up real quick, and it's going to be like a 40 by 60. You know, didn't mean to do that. Say it's going to be a 40 by 60. And let's say we're going to use columns, W-beam columns. So there you go. So there's 40 feet. And typically, buildings, you know, that's the wrong way to do a dimension. Buildings can space things from center to center or from outside to outside, just kind of depends. You just need to always watch where your dimension line touches. And then of course we've got a center line right here going between that beam, center line right here between this beam, or I'm sorry, column. Again, these are columns. And then let's say this is a W10 by something. I'll just kind of make these up. I don't know necessarily if these weights are correct. I don't remember. I don't have them memorized or anything. But let's just say it's a W10 by 16, which means it weighs 16 pounds per foot. Its overall depth is 10 inches, and that's what we're going to use for this. And we will just say it's typical. Now the implication is if it's typical, then it might be the typical for all. But since it's pointing at a column, it means it's only typical for the column. And then we've got the beam. So let's just say this is a W16 by, I don't know, we'll just make it up another, W16 by 30. Okay. That's how it would show up on a set of plans. And steel fabrication with this is kind of how it goes. The plans show this bit of information, and there's a lot of other stuff that gets thrown in there with it that we can talk about connections a little bit later. But that's a W-beam. Very, very important for you to understand getting started on how this looks, and we'll take a look at another one here in a second.